Okay, this problem is going to be the additional problem on problem set 1, and this is a really interesting problem. So this is what we call a context-rich problem, and what I've done here is I've described basically you have a summer job, right, and you're working for a university research team, and your job is to basically launch a rocket and do so such that it accelerates upward at a constant rate using its rockets. After the fuel goes away in 30 seconds, it falls to Earth. And the whole process has to take place in 5 minutes. But your fuel expires after 30 seconds. Okay? So this is a challenging problem. There are no bones about it, but it incorporates a lot of things that we've already talked about. It might not seem like it yet, but let me sort of sketch out how I might think about this. So I think it's useful to break this problem down into two different problems. So let me sort of sketch out. So this is the additional problem for problem set 1. Okay, and here's roughly what the motion looks like. So let's plot the height y as a function of time. All right, I'm going to try to make it, roughly to scale here. So after 30 seconds in the problem, the rockets turn off. So during that time that the rockets are on, the rocket first, it starts at rest at the ground. So we're going to say that this is 0. This is the ground level, and the rocket accelerates up. And if it accelerates at a constant rate, that looks like a parabola. And so it accelerates, and we don't know what rate it is yet, but it looks something like that. Kind of a parabola. So at 30 seconds, so we'll call this the rocket time. All right. But then after that, it's essentially a free fall problem. But here's the tricky part. Right at 30 seconds, the rocket still has some velocity going upward, positive. And so very slowly, the rocket begins to slow down and then come back around. And so the curve kind of looks like this. Okay. But this is a free fall problem afterwards. Okay. So it acceleration up, acceleration in the positive y direction, and then it turns around. The acceleration here is going to be negative from 30 seconds onward to a total of 5 minutes, which is 300 seconds. Okay. Now, another way to think about this is to think about what the velocity does as a function of time. So I'm going to look at the velocity in the y direction as a function of time. Oh, this is time up here. And here's also what we see. So we know that the acceleration is positive during the rocket time. And so the velocity is increasing. All right? And so the velocity goes up. And then when free fall takes over, when gravity takes over, the velocity, it's still positive for a while until we reach this sort of turnover point. But it decreases, and then at the top, the velocity becomes negative until it crashes into the Earth at some time, okay? So that's what the velocity looks like. And then we look at the acceleration in the y direction. And the acceleration, well, the acceleration for the first 30 seconds, it's positive, it's upward. And then after that, for the remainder of the trip, it's negative. So there's this jump here. Now, I probably got sort of the details of the motion and the exact velocity, the size of these velocities. I probably got that wrong, but qualitatively, that's what this problem looks like. All right, so that's the first step, is understanding what we're doing. It's actually two problems. Okay, so the other challenging thing about this problem is that we don't actually know at the outside what the acceleration of the rocket is going up, and that's what we're asked to find. And so this is a problem of organizing information and figuring out what we know. Okay. And so here's what I'm going to break this thing down into two steps: the rocket step and the free fall step. Okay. And during the rocket step, the acceleration is positive. I don't know what it is, but I'm going to call the acceleration A1. All right. I don't know what it is. Okay. The initial position is 0. It starts at the ground. And at some later time, T1, which we know is 30 seconds, it reaches some position after which time the acceleration due to gravity takes over. So it reaches a height, I'm going to call it y prime, after 30 seconds. That is given by 1/2 the acceleration times t1 squared. So that's the height it gets after 30 seconds. So I can just basically plug that in, but I don't know what it is because I don't know the acceleration yet. Okay. Well, here's the other thing that I know. I know that the velocity is linear. Let me pull this back in here. Okay. I know that the velocity for the first 30 seconds is linear with a positive slope. That slope is the acceleration. So the velocity when the rocket turns off, well, it's going to be whatever the acceleration was times the time. Okay? And that's quite a bit of information. Now again, we don't know a lot of this stuff yet, but we're going to need this stuff because now when we go to the free fall problem, that is when we start here, well, now we know some stuff. Okay? We know that the height is going to be, well, whatever it was when the rocket turned off, plus whatever the initial velocity was. And I'm going to call this, this is some time, after the rocket turns off, t, plus 1/2, and the acceleration now is the acceleration due to gravity, and that's minus, I'm going to call it 10. That's 9.8 meters per second here, but I'll call it 10 meters per second just for the sake of simplicity, times t squared. And that'll give me the position as a function of time. And so basically what I'm saying is that the time from here on, all right, is given by, the height is given by this expression. This is a constant acceleration problem. Okay, but we're breaking it down into two problems. And here's what we want. We want at the bottom, well, that's a particular time later. And we know that since the whole thing has to last 5 minutes, if it takes 30 seconds to get to the point where the rocket turns off, we know that at some time, t2, well, that's 5 minutes minus 30 seconds, which is 270 seconds. So after 270 seconds, after the rocket turns off, that is when it crashes. And it crashes when y is equal to 0. That's the condition for when it hits the ground. So again, it's not quite clear yet. We have everything we need, but what I'm going to do is I'm going to take this expression and I'm going to plug in some stuff, all right? I know that 0 should be y prime, the height when the rocket turned off, plus v prime, the velocity of the rocket right when it turns off, and some later time t2, well, we know that's 270 seconds. Oh, there we go. Now we're getting somewhere. Plus, well, I have a minus 10 over 2. That's actually minus 5 plus negative 5 meters. I'm sorry, this is meters per second squared up here. Minus 5 meters per second squared times, again, 270 seconds squared. Okay. Now we're after the acceleration here, A1. And so here's the interesting thing about this. So again, it's not clear that we have everything we need yet, but if we just start plugging stuff in here, 1/2, I'm going to put A1 over 2 times T1. Well, I know what that is. That's 30 seconds squared. V prime, well, that's A1 times 30 seconds. That's this first term here. I'm sorry, what was I doing here? V1, oh yeah, so this is plus V1 times, this is 270 seconds, so that's this next term here. So that term, minus 5 times 270 seconds squared. And the really interesting thing about this, and again, it's kind of hard to tell right now, but you know, I have this thing, so I'm going to calculate this. I have my trusty calculator right here. I'm not sure if you can see this in the video, but whatever. So 300 squared divided by 2 gives me 30 squared divided by 2 gives me 450 times A1 plus 30 times 270, 30 270. I don't think I did anything wrong here. Maybe I did though. A1 minus 5 times 270. 5 times 270 squared. So that's a pretty big number, right? So that's 364,500. Okay. And so what I'm going to do is I'm going to combine things out here. So I have 450 plus 8,100. So that's 8,550 A1 minus 364,500. And I can solve this now. So A1 is going to be 364,500 divided by 8,550. Again, I'm going to plug that in, divided by 0. And unless I made a huge mistake, I find that the acceleration has to be about 43 meters per second squared. And that's roughly 4 times the acceleration due to gravity. Okay. So again, just to kind of recap what we've done here is we broke the problem down into 2 parts. All right. We plotted out. We've tried to visualize what the position, velocity, and acceleration are doing, and then we kind of struggled our way through. I didn't know how to I didn't know how to work this at the beginning, but I didn't let algebra scare me off here. I didn't let things that I didn't know bother me yet, because oftentimes there's a relationship that's hidden in these problems that it takes some work to get to. And there's some math here. There's a final result. I don't think I made any math mistakes, although I'm gonna after I stop recording, I'm gonna check. But I think it's okay. That seems right to me because I know that these rockets accelerate quickly. But here's the thing: is that if I didn't accelerate enough, then I wouldn't be high enough. If I accelerated too much, I'd be too high. So this 300 second mark, it kind of makes sense that as I work through this, that I should find, in the end, some relationship that makes sense. Okay, there should only be one value of the acceleration for which this works. Okay? All right.